All right, thank you for coming, everyone. My name is Andrew Wang. I'm a PhD student at the University of Melbourne, and this work is presented with Simone Dudane, Meredith McCaig, and Andrew Perfors, and the work is Core Words in Semantic Representation. So, one of the big questions in cognitive science is, what is the nature of semantic representation? How are word meanings represented in the mind? One prominent approach is known as the distributional semantic approach, or distributional semantic models. And this typically involves information about words that occur close by to each other in their linguistic environment. And then this can be represented in a multi-dimensional semantic space where words are vectors or points in that space. And this approach is the foundation for large-scale computational models like GPT-3. A contrasting approach involves constructing semantic networks based on word association data or similar sources of data. And this approach goes all the way back to the hierarchical network model of Collins and Quillian. And so in this approach, words are represented in an interconnected network, and semantically related words are linked together in that network. So although the distributional approach is closely tied to natural language and word associations are commonly represented in a semantic network, this doesn't have to be the case. So you can encode word associations as a distributional model, and you can construct semantic networks from natural language data. So we draw a distinction here between the format, the architecture of the representation, and the content that the representation encodes, or the data that the representation is built from. And we focus here on the content or the data. And in this way, the accounts differ. One of the main differences between the accounts is in the extent to which they incorporate communicative factors. Language-based distributional models reflect the use of language for communication, and our communication is shaped by all sorts of pragmatic considerations that dictate the way that we talk, the way that we speak. For example, if I asked you to refer to this thing on the right, you would very likely call it a banana. You wouldn't call it a yellow banana, even though yellow is arguably quite central to the meaning of the word banana. In fact, you'd be more likely to utter the phrase a green banana than yellow banana, because that's something that's informative, that's novel. And so it's almost as though the things that are key to the meaning of words are the things that are less likely to be said. And so word association models capture the kind of multimodal sensory experiential information that is so important to word meaning, but that tends to be left out of natural language because of its role, because of its primary role for communication. But what these models do have in common is that they both share the idea that words depend on each other to get their meaning. And so inevitably this means that some words will be dependent on more than others. And so we can start to identify core words that are dependent on the most for their meaning. And these are words that are going to be important for semantic representation in some way. They might serve as hubs for information to flow through, or they might connect lots of different words into semantic representation, or they might be easier to access, but they're going to be important for semantic representation in some way. So these theories would differ on what the core words would be. So in word association networks, the core words are going to be the central words in the network, and so we can measure this using graph theoretic measures of centrality, and a very simple and straightforward one is known as in strength. It measures how many words are linked to the most other words, and so it kind of picks out these hubs of association that connect lots of different words in the network. In distributional models, we can the core words are the ones that occur the most frequently in the linguistic environment, and we can measure this using a measure of corpus frequency through natural language data. And this is directly analogous to the in-strength measure in the word association networks. And we can also think about the process by which the networks are built up. So for example, the preferential attachment hypothesis proposes that semantic networks are built by attaching new words to existing words in the network. And so in that account, the core words would be the earliest acquired words in the network. And so what I'm showing here is the top 10 core words on each of the three measures. And you can see that they capture the essential characteristics of the different approaches. So for example, the in-strength words, they reflect words that are very psychologically salient or that represent important semantic categories. The word frequency words are words that are highly frequent in communication. They're very polysemous and they're very communicatively versatile. They can be used in lots of different ways. And of course, the AOA words represent words that are important for young children. And so we can use core words to adjudicate between these different theories of semantic representation. This idea of core words parallels and is somewhat inspired by studies of core vocabulary in linguistics. For example, the Semantic Primitives Project tries to find a universal set of fundamental human concepts that are sufficient to define every other word in a language. And there's work on looking at dictionaries to see if there can be a set of words isolated that can then be used to understand the rest of the words in a dictionary just through looking up definitions. But these existing ideas of core vocabulary tend not to have been based on psychological theories of language, nor have they been empirically tested to see how well they account for human behavior. So the combination of theories of semantic representation that account for human behavior, plus the work on core vocabulary that aims to find the most important words in a language, leads to our study. And so our aim was to use a word guessing game to see which type of core words provides the best account of word meaning in the mental lexicon. And to that end, we had two research questions. Firstly, which core words would be the easiest to guess target words? And so we chose different target words that were chosen to be more core on each of the respective measures. And we also had an additional condition that I won't talk about that much because it didn't turn out to be very important in the end, but an additional condition with target words that were equally core across all three of the measures. And our second research question was which type of core words would make the most effective hints to guess target words from. So for this, we had different hints that were drawn from the different lists, the different measures of the core words. And I'll explain more of this in more detail. So we gave participants a task where they tried to guess computer passwords that were told were just a random English word based on a series of password hints. So a typical trial might look like this. You would see the first hint, which might be something like dinner, and you might guess something like eat. Eat's not the answer, and so the guesses would appear here, and the participant would see the next hint, which is water. You might guess something like meal. And that's not it either, so we see the next hint, and at that point you might guess fish, and so fish is the right answer. So that's how the trials would work. We recruited 500 participants from MTurk, and each participant saw 24 experimental trials, and the factors were manipulated within subjects. So each participant had 6 trials from each of the 4 different target conditions, crossed with 8 trials from each of the 3 hint conditions. And we also had 2 non-experimental catch trials that were designed to be easier, just to check that participants were paying attention to the task. For the target words, we had 4 different target conditions with 24 target words in each condition, and then we chose a random subset out of those for each participant. And we had 3 target conditions with words that we were more core on one of the measures and less core, but equally so, on the other 2. So over here you can see some of the example target words, and so for example, grandma is a word that is very early acquired by children, but it's not very high on the int strength measure, and it's not a very frequent word. So those are the first three target conditions, and we also had a fourth target condition with words that were equally core across the three of the measures. For the hint conditions, we had three hint conditions which were basically lists of the top 300 words of each measure, and we sampled hints from those lists for each of the target words. And so for each target word, we drew sets of hints from each of the three hint lists. And the way we did this is that we chose the top 6 most semantically similar words to the target word to be the hints for that target word. And we did this in one of two ways. So we had two different ways of calculating semantic similarity. We had random walk similarity based on word association data, and that's a way of calculating similarity in a word association network. And that was done using the small word of words data. And we also calculated semantic similarity using cosine similarity over word embeddings using word2vec. So what I'm showing you here is on the y-axis, the mean accuracy for the target words in a given condition. And that's being compared across the 3 experimental factors. So I've got target condition on the x-axis. The colors represent the different hint conditions, and I'm comparing them across the 2 semantic similarity types. So overall, the task yielded quite low accuracy. So across all of the trials, the accuracy came out to be 27.8%. There was no difference between the hint conditions. So you can see within each set of these bars, they're very similar in terms of accuracy. But there were significant differences between the target conditions, with the highest accuracy for in-strength target words. So you can see the accuracy for in-strength target words is higher relative to the other conditions. And there was no systematic advantage for congruent target and hint conditions. So that means that the same hint condition and target condition didn't yield an advantage in accuracy. And so those were the results for random walk similarity, and the results were qualitatively the same for word2vec. So there was another sort of result is that there was high accuracy for the ROW hints compared to word2vec hints. I'm going to speed through this a bit. So the picture so far is that in-strength words were higher in their accuracy compared to the other target words, but we wanted to know if this could be explained by some of the key factors to do with semantic representation. So the target conditions differ in the part of speech that makes up the target words. For example, you can see that there are relatively more nouns in the in-strength condition relative to some of the other conditions. And nouns were more easy to guess in general. So the question is, does this explain the accuracy, the higher accuracy for in-strength words? And we can see that even when taking part of speech into account, in-strength words are still higher. So for example, you can see just by looking at the nouns, they seem to have higher accuracy still. So again, we wanted to see if the high accuracy for in-strength advantage could be explained by semantic similarity. And there are 2 ideas here. One is the similarity between the hints and the targets. So to target words with more semantically similar hints, they guess more easily. And another is hint interrelatedness. So the idea is that target words with more semantically distinct hints should be easier to guess. Okay. What we found was that hint target similarity predicted accuracy, but only for the random walk similarity. and hint interrelatedness did not predict accuracy. So just looking at hint target similarity, we found that higher accuracy for in-strength words wasn't due to hint target similarity, because target differences in hint target similarity between the target conditions didn't favor in-strength, but they favored AOA target words. And we found that even after accounting for hint target similarity, in-strength words were still higher accuracy overall. So to recap the results, we found that target condition but not hint condition affected accuracy. There was no difference between the target conditions, but we found the highest accuracy for in-strength target words followed by AOA target words, and that could not be fully explained by part of speech or semantic similarity. So there was an asymmetry between the words that were being guessed relative to the words being used to guess, and that was something we didn't expect. That suggests that what matters is how easily the target words emerge during the search, as participants search in semantic memory for the target word rather than the points from which the search begins, that is, the hints. So it seems that what this task measures is coreness in terms of which words are more easily accessible, and that might suggest that those words occupy a central or prominent position in the semantic representation, in lieu of being easy to access. So words that are most central in word association networks are more easily accessible in the semantic representation, and they are more cognitively prominent, they come to mind more easily, and that might suggest an advantage for these word association-based models compared to the distributional models. And the lack of difference in hint condition combined with the low accuracy overall suggests that peripheral words may still have an important role to play in semantic representation. In terms of limitations and future directions, we would like to test different types of hint lists. For example, what happens if we use hints drawn from, if we expand the pool of hints and draw them from non-core words or the list of all vocabulary items. We would like to test different coreness measures. So what we have here is what we consider a good first approximation of our research question, but we would like to expand the set of measures that we can use. And we would like to use alternative tasks to investigate different types of coreness. So, for example, looking at coreness in terms of word predictability in sentence context, or in terms of navigating through a semantic network. And that's it from me. So thank you very much for listening. And here's my email and the link to the paper. Thank you.
Hi, really cool talk. Could you remind me how the networks of semantic association are built?
Sorry,
how the networks of like associations between words that ended up being good predictors of coreness, how those are built by researchers?
So they are constructed from word association data. So this is, well, at least in our case, that's data where just using a word association task with where participants are prompted with a cue and just told to freely respond with words that they associate with the cue, and then that association data is used to form connections in the network, and then you can build a network out of that, and then you can calculate statistics like which words are central in the network or which words are linked to the most other words in the network.
Thank you.
Thank you very much.